Okay. There you go.
Should be good. You can swap. And let me double check before you start.
Mm-hmm.
You're good.
All right, we're gonna start now. Welcome to ML Mondays. I'm Shriniket. You can call me Srini for short. And tonight we're doing ML Mondays lecture 6, and it's about building and training neural networks with Keras. Quick show of hands. Did any of you guys come to the first Tensorflow? Okay, so we got 3. But that's okay. For anyone who's joining for the first time, I have a recap slide so we can go over what you guys missed. These are the 4 lectures. I'm on the end with a really big name, but just call me Srini. That's Alvin, and then we got Karthik and Siobhan. Okay, so just a reminder, ML Mondays is just our weekly machine learning lecture series. We go from pretty much like beginner to intermediate, and we start with the foundations and we build up each week. Tonight, we're right in the middle of our TensorFlow block, and it's just the one where things almost start clicking for everyone. You can reach me, Alvin, or any of the other 2 through Discord, email, Instagram, and all the links are in our link tree as well. And the slides go up on the Google Drive after every lecture, and we post the recordings on YouTube. So if you guys want to check that out. Okay, so let's start with a quick recap of what you guys missed last week. So last week's lecture pretty much laid out the 5 foundational ideas, and I want to quickly walk through it. First is that TensorFlow is Google's open source numerical computational framework. It's not just like a deep learning library, but it handles pretty large scale math, hardware acceleration, and distributed training across like GPUs and TPUs as well. And second, tensors. Just what is a tensor? Tensor is a multidimensional array of numbers. A single number is a rank 0 tensor, which we call a scalar, and a list of numbers is rank 1, which is a vector. For example, a 2D grid is rank 2, which is a matrix, and then an image which has like height, width, and color channels is rank 3. So everything in TensorFlow is pretty much like your data, your weights, your predictors, your predictions. Everything is a tensor pretty much. And third, we have eager execution. In modern TensorFlow, operations pretty much run immediately when you write them, and it's just like standard Python. There's no need to like define a graph, for example, and then like run it separately. But this makes it much easier to write and debug code. And fourth, we have automatic differentiation. TensorFlow pretty much tracks every operation you perform, and you can automatically compute the gradients of your loss functions, for example, with respect to every parameter you put. And this is what makes the training possible, and it's the engine of backpropagation, which we looked at previously. And fifth is the ecosystem. The ecosystem, Keras, which we'll be looking at today, is the high-level building API. And TensorFlow, pretty much visualizes the training, and TF Lite runs the model on mobile, if you want, and TF Servings deploys them during production. Quick check. Can anyone remind me what a tensor is? Yeah.
Multi-dimensional array of numbers.
Yeah. That's pretty much it. Tonight we'll pretty much just take a look at all 5 of those ideas and use them to actually build something. All right, so building models with the Keras API. So Keras is TensorFlow's high-level API for building neural networks. It's been part of TensorFlow since version 2.0, I think, and it's pretty much what everyone in the industry uses on a day-to-day when working with TensorFlow. You access it through something called on your code tf.keras, or by importing Keras itself directly from TensorFlow through your code. The core tool in Keras is, I would say, the sequential model. When you build a sequential model, you're saying, data flows through this network in a straight line, and input enters and then passes through each layer pretty much one by one, and it comes out as the output. No branching, no skipping. It's just a pipeline. You pass, I would say, a list of layers. Each layer knows how to receive the input, and so it's like a layer. Each layer knows how to receive the input from the one before it, and the first layer is the one that needs the input shape, and Keras pretty much infers all the shapes after that automatically. So it learns layer by layer. And after you pretty much build the layers, you call something called model.compile. It's a function, and this is where you pretty much specify the three things that TensorFlow needs to run, which is the optimizer, which controls how the weights are updated, the loss function, which pretty much measures how wrong your predictions are, and the metrics, which are pretty much what gets printed during training, so you can monitor your progress throughout. After compiling, model.summary, another function, gives you almost a formatted printout of every layer. So you get its name, its output shape, and the number of trainable parameters. And always run this as like a quick sanity check. You want to make sure the model looks exactly like what you intended it to look before you start training it. I have another question. So why do you think we separate the building of the model from compiling it? What do you guys think the logic is behind that? Any guesses is okay. Yeah.
Is it that you don't want it to work on itself or build on itself or get confused with itself? I don't know.
Close. Yeah, that's along lines. Pretty much the building of the model pretty much defines the architecture, and compiling it defines its learning strategy, how it learns. So you might want to test multiple different optimizers or loss functions on the same exact architecture, keeping them separate so the mistakes are clean and easy. Okay, so layers and network architecture. So a neural network is just a fancy way of saying it's just a chain of layers. So each layer takes a tensor as input, applies some sort of mathematical transformation, and produces a tensor as the output. So that output is now the input for the next layer, and on and on and on. So the most fundamental layer is dense, also called a fully connected layer. In a dense layer, every single neuron is connected to every neuron in the next layer as well. So you create one with pretty much two key arguments, the number of units, which is how many neurons it has, and the activation function. Two other more important layers to know for today are dropout and batch normalization. Dropout is just randomly zeros. It randomly zeros out a fraction of a neuron, which outputs during each training step. And you specify the dropout rate. So for example, 0.2 means 20% of neurons are switched off randomly during each step. So the key reason why this works, if you guys might be confused, is that it forces a network to not just rely on one specific mean. So there's no redundancies or redundant representations spread across many neurons, so you don't want it to think something else. But we'll dig into why this fights overfitting, which is what we call it, in a few slides. So pretty much batch normalization just pretty much normalizes the activation within a layer across the current batch of training examples. This tends to make the training more stable and faster, and it's especially useful in deeper networks. And as for the network size that we talked about, the depth of your network, which means pretty much how many layers, and the width, meaning how many neurons per layer, are architectural choices. So deeper and wider networks can learn more complex patterns, but they need more data and more time to train and more prone to overfitting. When we go through the demo, I'll show you guys exactly what I mean. If you guys missed, they're the other two lecturers. I'm going to call them out really quick. Say hi.
Wait around for the rest of the class.
Yeah, I didn't get a round of applause. Okay, we'll move on to activation functions. So, and activation functions are pretty much what gives neural networks their power. So here's the key insight pretty much. Without them, a neural network, no matter how many layers it has, is just a linear function. It has nothing. So you can mathematically collapse the entire thing into a single matrix multiplication. And the activation functions introduce what is called nonlinearity, this is what allows the networks to learn more complex real-world problems. The most widely used activation function in hidden layers is a ReLU, which is a rectified linear unit. It's pretty simple. If the input is negative, the output is 0. If it's positive or 0, then the output value is remained unchanged. So ReLU is fast. It's really fast to compute, and it avoids certain training problems, like vanishing gradients, for example, and it works really well in practice. But it's pretty much your default choice for hidden layers that you want to use. And for the output layers, the choice pretty much depends on your task. For binary classifications, for example, predicting yes or no, spam or not spam, you use sigmoid. And sigmoid pretty much squashes any input to a number between 0 and 1, anything binary, which you pretty much interpret as a probability. So 0.9 means the model is 90% confident that it's the positive class. And for multi-class classifications, predicting one of several categories, you use something called softmax. So softmax takes a vector of raw scores and converts them into a probability distribution that sums up to 1. So each value pretty much represents the model's confidence in that particular class. So the predicted class is one with the highest probability. So tan h, also, the hyperbolic tangent, outputs values between -1 and 1. It's pretty less common for feed-forward networks today, but it's still used in recurrent order architectures. One thing I would let y'all take from the slide is a rule of thumb. ReLU in hidden layers, softmax for multi-class outputs, and sigmoid for binary outputs. That's it. So I have a scenario for you guys. So let's say you're building a model to recognize handwritten digits. So like 0 through 9, something that's handwritten. How many output neurons do you think you need? It's really simple. 10? Yeah, 10. It's straightforward. Okay, let's move on to loss functions and optimizers. Okay, so the loss functions is how the model measures how wrong it is. So you don't want the model to think it's keep going right, and when you go to look at it, it's completely wrong. So it's a good measure to see how wrong it is. If it pretty much takes the model's predictions and the true labels, and it returns one single number. And the lower that number, the better that model is doing. So 0 means perfect predictions. And during training, everything is oriented around minimizing that number as much as possible. So for regression tasks, predicting like a continuous value, like house prices or temperatures, you use like a mean squared error, for example, and it pretty much squares the difference between the prediction and the true. Yeah.
Will these losses ever be negative, or it's always going to be positive and we're trying to get it towards 0?
I think mean squared error will always be strictly positive.
Yeah, it's always positive.
Because you calculate like the Euclidean distance, right, between the points.
Yeah, there's a lot of math
So
involved.
you're always squaring the values and then square rooting it. So you always get strictly positive or non-negative value at least.
Yeah, you square the difference between the prediction and like the true values, so it would never be negative. Okay, yeah, so moving on, we have binary classification. You use binary cross entropy, is what it's called, for multi-class classifications with like integer labels, for example, which is what we'll use tonight for our demo. And you use sparse categorical cross entropy for if your labels were like one hot encoded instead of integers, you'd use categorical cross entropy without the sparse. And once you have a loss, you need an optimizer. And optimizer is just an algorithm that adjusts the model's weight to just reduce that number. And the optimizer uses the gradients Tensorflow computed automatically through backpropagation, which we talked about in the last lecture, and applies them to update every weight in the network from then. So we got ADAM, which is one of the it's a adaptive moment estimation. It's the go-to optimizer for almost everything. It adapts the learning rate for each parameter individually based on how the gradients behave across the training steps. So in practice, it pretty much converges faster and just simply more reliable than the other methods. When you're not sure what to use, just use ADAM. And we have also SGD, stochastic gradient descent. It's pretty much like the classical method. It updates the weights based on the gradients of just a random batch of examples. It's pretty simple and it's very well understood. I'd say some experts prefer carefully tuned SGDs for production systems, but for learning and for most applications, you would want to use ADAM. Okay, so now we got training a model fit. Okay, so model fit is the function that runs the training. So you pass it on pretty much 4 core things. One is your input data, your X, your labels, your Y, the number of epochs, and optionally a validation split. So an epoch, if you guys don't know, is one complete full pass through of all your training data. So after each epoch, TensorFlow reports the current loss and any other metrics you specified. And if you set like a validation data, for example, it reports those too. So you typically want to train for multiple epochs and watch the metrics improve over time. So you don't want to do like just one run of the training instead, and the model's not going to learn it all in just one run of it. And next you got the batch size. The batch size pretty much controls how many training examples are processed before each weight is updated. So the default is 32. And rather than just waiting to compute gradients over like a full data set, which would be pretty slow and extremely memory intensive, the model processes like one batch at a time. So it updates the weight, then moves on to the next batch. And this is what you call a mini batch gradient descent, when you just process one batch at a time and update the weights and then move on. And next you have a validation split. Validation split is an important argument. Passing like a 0.1 reserves 10% of your training data as a validation set. So after each epoch, the model evaluates on this data without updating its weights. So this gives you like a live read on more generalization. So if your training accuracy keeps going up, but your validation accuracy plateaus or drops, which is very common, the model is doing what's something called overfitting, and it's not good. So the model fit pretty much returns what's called a history object. This is a dictionary. It's like a dictionary containing like the loss and the value metrics at every epoch. So for both training and validation, you can plot it directly to the visual learning curve. And we'll do this in the workshop as well. Okay. So evaluating and making the predictions. Okay. So TensorFlow gives you 2 key tools for this. Model.evaluate, the 2 functions of model.evaluate and model.predict. So model evaluate is pretty much just takes your test inputs and your test labels, runs a forward pass without updating the weights, and then returns the loss and the accuracy on that test set. So you always pretty much evaluate on data that was never used during training. That's the most important part. So this is like your true performance number on your model. It tells you like how the model will perform in the real world. And then you got model predict, and this pretty much just takes inputs, no labels, and then returns the model's raw outputs as a NumPy array, for example. For a softmax output layer, which we talked about in the previous slides, let's say on like a 10 class problem, where each row of the output is a list of 10 probabilities, summing to the number 1. The model is actually saying that I think, like for example, I think there's a 97% chance that this is a 7, and a 2% chance if it's that it's a 1, and so on. It's just guessing. To get the predicted class, you run something called NP argmax. It's another function. We'll get into it on each of the outputs row. So, which pretty much picks the index with the highest probability. And next, there's 2 metrics to always pay attention to. Is the training accuracy, which shows how well the model memorized the training data, and test accuracy to show how well it generalizes that. So the gap between these 2 numbers pretty much tells you how much the model is overfitting. So a small gap between the 2 is pretty healthy. It's nothing normal. It's pretty normal. But a large gap means that the model learned the training data way too specifically, that it's not able to generalize it to the real world. All right, so understanding question. Your model has like a 98% training accuracy, but only a 72% test accuracy. What does that tell you? And what is something that you would try? Yeah.
It's overfitting, so you might need to like increase your data set, like use a bigger data set.
Yeah, that's one example. And that's pretty much like one of the fastest fixes. Or you can add something called a dropout layer. It's like probably the fastest fix, and it's really easy to add in a Keras model. Okay. So overfitting, we talked a lot about it, and we'll talk about how to prevent it as well. Okay, so overfitting happens when a model learns the training data way too well. So it includes the noise and the specific quirks of that particular data set. It memorizes that too. And pretty much as a result, it fails to generalize to new data it has not seen before. So pretty much, I guess, an example would be, think of it like a student who memorizes every single past exam, word for word. Like the previous exam for like your chem class or whatever, they memorize all the previous exams word for word, but the new exam's not gonna have that as the exact answers. So it's pretty much that, but in a different angle. So they're stuck because they don't know they only learned the specific answers and questions of the previous ones, but not the underlying concept of what that exam is teaching you. And that's exactly pretty much what an overfit model is doing. The signature of overfitting is just a gap between the training and the validation performance, essentially. The training accuracy keeps climbing towards 100, so you think the model's doing good, but the validation accuracy just stops improving, or in the worst case, it gets worse. That divergence should be a warning sign, and there are 4 main tools to fix this. One, dropout is the most commonly used. During each training step, the dropout randomly sets a fraction of a layer's output to 0. The model can't rely on any single neuron consistently, so it removes the model from overfitting. So it's pretty much forced to develop redundant paths. So like multiple neurons that capture the same patterns, and this result is a bit more robust, so it more generalized model. And at inference time, the dropout is turned off automatically. And next you have early stopping. Early stopping pretty much monitors your validation loss during training, and when the validation it stops improving for a set number of epochs, which you can put in the code. Training pretty much just stops automatically, and this prevents the model from continuing to overfit long after attack. And then next you have L2 regularization. And this pretty much adds a penalty to the loss function based on just the magnitude of weights. So it pushes the optimizer to keep the weight small, and which prevents the model from becoming way too sensitive to any individual feature. And by simply just gathering more data, for example, like you said, it's often the most effective way and the most effective solution. Trained model on more diverse data, with varied examples, has a harder time just simply memorizing and overfitting. And the relationships it learns have to be more general. So everything it learns has to be more general, and it's a good rule of thumb to just use more data if you're stuck. Okay. So introductions to CNNs. Okay, so CNNs are the most dominant architecture for anything involving images, for example. So if you've interacted with facial recognition, self-driving car vision like Tesla, medical image diagnosis, or even a photo search, there's almost always a CNN at the core. So CNN is a convolutional neural network. And the key insight behind CNNs is that the image have what's called a spatial structure. A pixel has a meaningful relationship to its neighboring pixels, and a dense layer pretty much ignores this completely. It treats every pixel as equal. It's equally related to every other pixel, and a CNN instead uses what's called filters, which are just very small, learnable matrices that slide across the image to detect the local patterns. Convolutional layer are where the actual feature detection happens. Convolutional layer doesn't just look at the image all at once. Each filter kind of detects one kind of local pattern. Edges in a certain direction, or there's a particular color gradient in that image, or a specific texture. Each layer in a CNN detects simple things, like the edges and corners. The later layers is when they combine into increasingly complex structures. And that's when the curves that they detect become shapes, and then the shapes become objects. So it slowly learns throughout of the image. And okay, so pooling layers follow convolutional layers. My bad, I didn't even see the slide where it moved. Okay, so pooling layers pretty much follow convolutional layers. What's called a max pooling, the most common type, slides a very small window across the feature map and keeps only the largest value in each window. So this reduces the spatial size of the representation and fewer numbers to process, and it makes a model more robust to very small shifts in where the features actually appear. And after a series of convolutional and pooling layers that you do, the feature maps are pretty much flattened into a vector, and it's passed to a dense layer for the final classification. So exactly like the networks we've been building, we're going to build tonight as well. In TensorFlow, you build these with something called tf.keras.layers.con2d. And tf.keras layers max pooling 2D, for example. Those are functions. Tonight we'll pretty much just use a simpler dense network for our workshop, which still gets about 98% accuracy. And in a future lecture, we'll come back and build a CNN for the same task and see how much further we can actually push it. Okay, let's go to, if you guys can everyone open a browser and go to collab.research.com and just sign into your Google account and just open a new notebook. If anyone has any questions, let me know. Give me like a thumbs up when y'all are good. Okay, I think everyone's good. I'm gonna teach just a simple neural network. I'm gonna teach this a very simple rule: y equals 3x plus 1, and we'll give it 6 pairs of numbers, let it train, and ask it to predict a value that it has never seen before. So the whole thing is just pretty much 5 cells, very simple, and we'll go 1 cell at a time. So first, let's import Tensorflow as TF and import NumPy. So that's all we need. Just TensorFlow is the framework. It handles everything from building the model to running training, and we use NumPy for creating our data arrays. And just type this into your first cell, and we can just click the run to make sure it runs. It'll take a couple seconds as it connect to the. Okay, so next for cell 2, we'll do these 6 pairs of numbers. We'll put it's going to be our training data set, and let's write the code right now. So let's say access equals np.array. These will be our training data set numbers. So -1, 0. We'll do 0. Let's see, right? Okay. 1, 2, 3, 4. Yeah, 4 should be good. And then these are float numbers. And then we'll do a ys ins np. And we'll do -2, 1. Yeah.
Is that -0.1 or?
Oh wait, that's supposed to be -1.
Oh.
One.
Does it have to have a point thing?
Yeah. We're inputting it as a float. 4, let's say 7. 10. 13. Okay. Yeah, so these are the 6 pairs of numbers that we're going to use for our training data set, and the XS and the YS are just inputs. XS is just the inputs, and the YS are the correct outputs. So this is how we're going to train it. We're giving it the correct inputs and the correct outputs for it as well. The hidden rule connecting them is the formula that I just said, y equals 3x plus 1. You can check it yourself, plug in like x equals 2, and then you get 3 times 2 plus 1, which is 7, and then blah, blah, blah. So it doesn't know that, but we're going to train it to understand and learn. Okay, let's run this. And then now we'll actually build and compile the model. This is where Keras comes into play. So.
What does D type mean?
It's just like a float. It's like that's why you use a 1.0. Like we're giving it like the decimal values. Is pretty much it.
I think you might have spelled sequential wrong.
Oh, yeah.
That's alright. It's just like typo.
Sequential. Okay. We'll compile the model as well. Optimizer. D. Yeah, so we talked about SQD and mean squared error before, but to reiterate, like sequential, first of all, like the sequential means the layers are stacked in a line and the input flows, through each one. And we have just one layer here, just a dense layer with one unit, meaning there's only one output neuron. And the input shape is 1, which tells the model to expect just a single number as the input. This is the simplest possible neural network, just one neuron in and just one number out. And model compile is where we set the learning strategy. So the optimer SGD stands for, again, stochastic gradient descent. We talked about this. Just a classical method that just nudges the model's weights a little in the right direction. And the mean squared error is the loss function. It just measures how wrong the model is by just squaring the difference, as we talked about before. Okay, I'll run that. Oh.
You spelled optimizer and SGD.
Oh my God.
It's alright.
Okay. You got like Grammarly over here telling me everything I'm doing wrong. Okay, now we'll actually train the model. We'll do model fit. We'll do, model fit. We'll set the epochs to 500, and then we'll print when it's done.
We set verbose equal to 1, will it print updates as we train?
Yeah.
Can we set it equal to 1 and see what it outputs?
Huh?
Can we set verbose equal to 1 and see what it outputs?
Yeah. Yeah, you can see how the loss just pretty much just goes down and down as more epochs. Okay. Now while that's running, I'll just tell you what I actually wrote in the code. So the model fit is just a training call. We just pass it our inputs XS and our labels YS, and we tell it to run for 500 times. And an epoch is like, again, one complete pass through all 6 training examples, the numbers we gave. So the model will see those 6 pairs 500 times, just adjusting to its internal weights slightly each time to reduce its loss. And you can see, it's at, it went from, I don't even want to scroll that much, but you guys can see. Well, again, like you said, verbose I use 0 because it doesn't print anything during the training. If you use 1, this is what it shows. Otherwise, like when I put 1, it just shows 500 lines of code that Collab just outputs. Okay, so now you see training is complete. Now we can move on to, we'll tell the model to make a prediction. So print. We'll do 10. Yeah. This pretty much just asks the model, if given an input of 10, what is your output? And the model's never seen the number 10, so it's a completely new number, and it's applying the rule that we talked about, just in a very small scale. So it doesn't know the equation that what their output is based off of, but after looking at the numbers 500 different times, let's see if it gets it right. Yeah, so if you give 10 to the to y equals 3x plus 1, it should give you 31. And it gave you 30.99. So just 30, yeah.
What if you did not get 31?
What did you get?
I got 33.4.
What was your loss?
Yeah. You see like the loss right there.
Her loss was only 0.7.
Hmm.
Did I mess it up?
Scroll all the way up. Just look for those two.
Sorry.
Oh yeah. Yeah.
Sorry.
I'll just wait. It's fine. Yeah.
Does it matter if you put capital letters?
31.00, is that close enough?
Yeah, 31's the actual answer. It just depends. It's like every model is different because we're using a collab environment that's it's cloud based.
I changed it here.
Is that?
Yeah, this
Does
is
that mean
the,
it
this,
did
the
change it?
red one was my old one when I misspelled it, and then the green one is the new one when it decided.
Oh, I
that
thought that
it was
means
wrong.
it's suggesting that change.
Yeah, and I clicked yes, I would like that change, but it's still showing me that I made a mistake.
Yeah.
So would it ever give you like the exact answer? Or
Yeah,
would
it gave her 31. It's just like depends because we only trained it 500 times on such a simple model,
Yeah.
on just a simple data.
So like with more epochs?
Yeah, more if you do like 10,000 epochs, yeah, it'll probably get it. Yeah.
But does it increasing the number of epochs also lead to overfitting sometimes?
Yeah, that's true. That's true.
So there's like a.
So there's good and bad to raising the epochs, but moreover, why I got 30.99 was just because the model learned from a very small data set. I mean, the data set was just like 6 different numbers, 7 different numbers.
You would also put the learning rate, right?
Yeah, learning rate is also something we could do. But there's always a tiny amount of uncertainty. If you've trained with more epochs, like she said, and or just gave it more data points, it would get even closer. But with more epochs, you risk overfitting. But 30.99 or anything close is like pretty remarkably good result for just 6 pairs of numbers and training it 500 times. And this is just pretty much the full TensorFlow workflow, just the simplest form, right? You import, you create the data, and you build the model, you compile it, then you train it, and it predicts. That's it. So every complex model you'll ever build, whether it's like a CNN classifying medical images or just a language model that generates text, they all follow this exact same pattern. And it's just, you just saw the foundation of all of it. So, one last question. Try changing the input, right? So for 10, what do you think the model will predict for 0? We'll do 0.0 and we'll run it. Now is that, so based on our function y equals 3x plus 1, if you input it 0, it would give you 1 as well. And it's close enough because, y, 3 times 0 is 0 plus 1. The model learned that too, even with the 0, even though the 0 wasn't even in the training data set. So we can try like a negative number too, like a -2. Yeah, so if you put a -2, 2 times 2 is 6, -6 plus 1, -5, and it's close enough. So because we put the negative number in the training data set, just one, we put -1, that's it, and it still is generalizing to this as well. So it's, again, very small data set with only 500 epochs, and it learned this much. So, imagine what it can do.
So if the negative number wasn't in the input set, it would have trouble with.
We can try. No, let's see. We'll do this. So I took out the negative inputs and the negative output, and let's see what it says from -2. Yeah, still got close enough. So, that should show you how well the model learns. Okay, so back to the slides. Okay, yeah, that's it. Great job. In one session, we pretty much went from theory to practice, and I hope you guys learned just the basics at least in between this. And if you guys want to look at the first lecture as well, it's always in our Google Drive to get more of an understanding. And just key takeaways. Keras gives you a clean and intuitive API for building the models with sequential and dense layers like we used. Activation functions introduced a nonlinearity that's pretty much what makes neural networks powerful. And your loss function and optimizer is what drives learning. And for overfitting, dropout fights it, giving it more data fights it. And the training loop, compile, fit, evaluate. And it's the same workflow that you'll use for every problem that you want to tackle using machine learning. And make sure you guys signed in. And if you guys want to see the link tree for the Google Drive or anything else, make sure to look at that. But that's it. Thank you.
Thank you.
Thank you.